Navigating the Bias-Variance Trade-off, a guide for data scientists, Instant Data Help Analytics Services. In the field of machine learning and data science, one of the fundamental challenges is finding the right balance between bias and variance in a model. This delicate trade-off, known as the bias-variance trade-off, plays a crucial role in determining the performance and generalization ability of a model. The bias-variance trade-off refers to the relationship between the bias and variance of a model. Bias represents the error introduced by approximating a real-world problem with a simplified model. It is the difference between the expected prediction of our model and the true value we are trying to predict. The bias-variance trade-off can be visualized as a U-shaped curve. On one end of the curve, we have high bias and low variance, which leads to underfitting. Underfitting occurs when the model is too simple to capture the underlying patterns in the data, resulting in poor performance. On the other end of the curve, we have low bias and high variance, which leads to overfitting. Overfitting occurs when the model becomes too complex and starts to memorize the training data, failing to generalize well to unseen data. Strategies for navigating the bias-variance trade-off. Simple models with fewer parameters tend to have higher bias and lower variance, making them less prone to overfitting. It is essential to strike a balance by selecting a model that is complex enough to capture the underlying patterns but not too complex to overfit the data. Regularization techniques help control the complexity of a model and prevent overfitting. Cross-validation is a technique used to estimate the performance of a model on unseen data. This helps in understanding the bias-variance trade-off as we can observe how the model's performance changes with different training and validation sets. Ensemble methods combine multiple models to improve predictive performance and reduce the bias-variance trade-off. Bagging combines predictions from multiple models trained on different subsets of the data, reducing variance. Feature engineering plays a crucial role in finding the right bias-variance trade-off. By selecting relevant features, transforming variables, or creating new features, we can improve the model's ability to capture the underlying patterns in the data. By selecting the right model architecture, using regularization techniques, employing cross-validation, leveraging ensemble methods, and performing effective feature engineering, data scientists can strike the right balance between bias and variance, leading to improved model performance and robustness.